Okay, so for anyone that just walked in, I've got assignment number 5 rated. I still have your assignment 4s, but 5 I got that. So let's see. What are the relevant announcements? So assignment 6 is out. That'll be the last graded assignment. And so that's April 3rd. So that's next Wednesday. There is a formal report will be due the week after. So that's April 10th. And then so if you're in the Tuesday lab section, we did day 2 of experiment 5, the last lab yesterday. If you're in the Wednesday section, we're going to do the last day of lab 5 today. So what I want you to do is, because we don't need to meet in the lab anymore, I want you to bring your experiment number 5 notebooks to class on Wednesday, April 3rd, and just hand them in at 11. And so that would mean that you're handing in your, I don't know, would you prefer if you were handing in your notebooks on Wednesday and then your assignment on Friday? I can do that if you want, instead of doing them both on the same day. Who wants them to be on different days? Okay, so let's see then. We'll make this one the 5th. And so I'll have to remember to do that, but I think that's easy enough. And then the last thing I wanted to say is, if you're going to sign up, if you're going to do a makeup lab, there are sign-up sheets. It's the same sign-up documents we've been using for the regular labs. I want you to sign up for those labs today, just so that we know what we need to set up next week. So there are sign-ups for makeup labs on Tuesday and Wednesday of next week, and Tuesday and Wednesday of the last week of classes. So why would you do a makeup lab? Well, one of the reasons is maybe you were sick or something during the term, you missed part of a lab, and so you could come make it up. If on the other hand, you're working on your formal reports and you wanted to repeat part of the lab, you could use the time to do that as well. And so I noticed that some people have already signed up for the makeup lab, so thank you for doing that. If you don't need a makeup lab, then obviously you don't need to sign up. Okay, good. Any questions about any of those details? Yeah.
Right, our formal report on next year where we didn't have perfect results, right? As long as we.
Yeah, I think so. Just like it's really the formal report is I want to see like good explanation of the physics and the data analysis and that kind of stuff. Yeah. So, if you didn't get H to 3 significant figures, that's not a problem. Yeah. Okay. So what we were talking about last time was this nonlinear fits stuff. And we had developed sort of a simple way of minimizing chi-squared. We couldn't do like a formal minimization using these partial derivatives because, well, we could do the minimization, but we couldn't isolate the fit parameters to figure out how we would optimize them to get the minimum value of chi-squared. So instead, what we're going to do is we decided We're gonna list all of the parameters that we are searching for. A1, A2 up to AM. We know something about the physical system we're studying so that we can pick reasonable ranges, reasonable allowed values for these fit parameters. And then we're gonna select some step size so that we can go from the minimum to the maximum in the range. In equal intervals of our parameters. Then what we're gonna do is where we evaluate. I don't know why the internet sucks in this room. I think I'm on. Yeah, I'm on the usual, I don't know, secure, whatever, Wi-Fi. Anyways, so we just take all the possible combinations of our a parameter values and just calculate by brute force chi-squared at every single possible value. And we're gonna search through our table, and whichever set of parameters gave the smallest chi-squared, that's what we're going to identify as our best fit parameters. So we kind of drew this sort of picture. If we were only doing a 2-parameter fit, we would have an axis of A values and an axis of A2 values, sorry, A1 and A2 values. And you know, you can imagine making a grid in this plane formed by the A1 and A2 axes. And at each intersection of this grid is where we calculate chi-squared, and then we draw a surface of those chi-squared values. And wherever that minimum sits, those are the parameter values A1 star and A2 star that are estimates of the best fit parameters. Okay, yeah.
Parameter.
Yeah.
What do you mean by parameter?
Oh, like in a linear fit, the parameters you're searching for are like the slope and the intercept.
Okay.
Yeah, yeah. There's unknown quantities that you're trying to determine from your experiment. Yeah. Okay, good. So what we haven't done is we haven't talked about estimating the uncertainty in the best fit parameters. Okay, so that's what I want to focus on today. So what we're going to do is we're going to start how we always start is we're going to imagine that we perform an experiment and we measure the usual thing. We always measure xi versus yi plus or minus sigma I for I equals 1 to n. Okay, so then we're going to fit our data to a model where y is some function of x and then these parameters that we're trying to find, these unknowns. Okay, and so however we do our fit, we determine a set of best fit parameters for A1 up to AM. And so maybe it's like this grid search that we were talking about. We do that process. Okay, so we fit our data to a model that depends on the parameters AK, where K is equal 1 to M. Then we find the set of parameters that minimizes chi-squared. Where chi-squared is the sum, it is yi minus y divided at xi divided by sigma I all squared, and then I is going to be from 1 to n, the number of measurements we've done. So that's everything we sort of already talked about. So we have at least one way of possibly doing these steps. Okay, Good. So what I want to do is I want to go back and I want to think about where this chi-squared came from. And if you remember back to when we were doing linear fits, the chi-squared definition is exactly the same. The way we got it is we said, okay, let's imagine that we wrote down the probability for if we're sitting at x1, what's the probability that we're going to measure y1? And it was this Gaussian probability, we called it P1. And then we said, okay, do the same thing for x equals x2 and x3 all the way up to xn. And so now we have all these probabilities, P1, P2, P3, and we said the net probability that we would get the data set that we got is given by the product of all these individuals. So let's just recall that chi-squared came from the fact that the probability of obtaining a set of data xi, yi plus or minus sigma I from our parameters, which are going to be like the A1, A2 up to AM, is given by. Okay, so this is some probability that depends on the values of these parameters. We adjust the parameters to maximize this product of probabilities, which was equal to this product from I equals 1 to n of these PIs. And these were all Gaussians. And so what we have is for our Gaussians, we had delta y, which is going to tell us the probability that y falls between y and y plus delta y. So just some narrow range band of values. And then the Gaussian distributions had a coefficient of 1 over sigma I, and then there was a square root of 2 pi in this denominator. So that was the coefficient. And then the Gaussian has an exponential, and there was a, I think I need a minus 1/2 in here. And then we had, let's see, yi minus y of xi over sigma I squared, like so. And I still need to close this bracket over here. Whoosh. I think that's it. And you can start to see this chi-squared developing in the argument of this exponential. What we're going to do is this product of exponentials turns into an exponential of sums, and the sum that we get inside here is the chi-squared. Okay, so let's just write that out a little bit. Well, the coefficient, we can't really do much with the coefficient. So we'll just have our delta y over sigma I square root 2 pi. That's just coming along for the ride. It's not going to be that important. But the exponential, instead of writing a product of exponentials, we could write that as a sum of one exponential, or sorry, one exponential with a sum in the argument. And that sum is going to be the sum of this thing. It's going to be the chi-squared. Okay, good. Sorry, if I want to match brackets, I would have this kind of thing. And all of this is exactly what we've been calling the chi-squared. And to maximize the probability, remember what we're going to do is, because this is a negative exponential, if we minimize the chi-squared, then that probability is as big as possible. Okay, good. So then what we have is that this probability that we're trying to calculate
is going to be equal to the coefficient doesn't change. But then we can express the exponential as -1/2 chi-squared. All right, so that's one thing that I wanted to remind ourselves of. And I'm going to call this equation number sign. We will probably refer to it again. All right. So where we're going to go with this is we're going to keep working on this expression a little bit, but we're going to focus in on the region where chi-squared is near its minimum. Okay, and so we could draw like an arbitrary chi-squared, and if it has a minimum, then of course, as soon as you move away from the minimum, you have to be going to increasing values of chi-squared. And what I want to see is what is the shape of chi-squared near the minimum? So we're going to try to determine the shape. The shape of chi-squared near its minimum. Okay, so minimization of chi-squared. Okay, so chi-squared is equal to this yi minus y of xi over sigma I all squared, and then we have to do the sum. All right. Now, this y of xi is a function of all of these parameters a1 to am in addition to x. And what we have to do is we have to think about the minimization of chi-squared with respect to each of these parameters. And so what I want to do is focus in on one. So suppose we have a set of best fit parameters where chi-squared is a minimum, and we're going to select one of them, like maybe the AK value. And we're just going to take that parameter and we're going to move it away from the value that minimizes chi-squared. And I want to see what is the shape of chi-squared when we do that. Okay, so let's Taylor series expansion of chi-squared about its minimum with respect to one of the A parameters. And let's call it, we'll call that parameter AJ. Okay, so J can be anything from 1 to n, 1 to m, sorry, if we have a m parameter fit that we're doing. All right, well, we know how to do Taylor series expansions, right? So chi-squared is going to be approximately, well, what is it? It's chi-squared evaluated at its minimum. Okay, so AJ star is going to be the value of AJ that minimizes chi-squared. Chi-squared. Okay, so that's the first term in our Taylor series expansion. And then what we have is a linear term, so proportional to AJ. And what do we need? We need the first derivative of chi-squared. So we would have the derivative of chi-squared with respect to AJ, and then we have to evaluate that at AJ star. All right, and I'm going to write out one more term. If we had a second term, we would have plus 1 over 2 factorial, but 2 factorial is just 2, so I'll just leave it as a 2. And then we have AJ minus AJ star squared times the second derivative of chi squared with respect to AJ evaluated at AJ equals AJ star. And we could keep writing more terms, right? We could have the cubic term and the n=4 term and so on, and keep going. All right, so question. If we're sitting near the minimum of chi squared, what is the slope of the minimum of a function? Zero, right? So, right, if you have a minimum and you draw a tangent line at the minimum, that tangent line is horizontal, it has zero slope, and that means that this first derivative, which defines the slope of the tangent line at the minimum, has to be zero. So this one has to vanish. Okay, yeah, sorry.
With no higher derivatives, that is.
No.
Oh, no.
No, so so remember, like the second derivative tells you the curvature.
Okay.
So if the second derivative is positive, what does it have? Negative curvature or something like that. So yeah, your higher order derivatives do not have to vanish. So at the minimum of chi squared, we require that d chi squared d aj, aj is aj star, would have to be zero, right? And so what we're imagining is if we made a plot of chi squared as a function of aj, you know, it could have some complicated shape. And so here's the minimum. We'll call this chi 0 squared. That's the minimum of chi squared. And this is aj star. And then if we were to evaluate the first derivative and draw its tangent line, it would be like this. This would be d chi squared daj at aj equals aj star. And the slope of that would be zero. Okay, good. Okay, so the other thing we could do looking at this expression is the first term is chi squared evaluated at the aj that minimizes the function. And so if we did that, we would just say, well, that's chi 0 squared, right? So this is going to be, we'll define this thing to be chi 0 squared. And so this is the minimum of chi squared. Okay, so then we could say chi squared is equal to chi 0 squared plus this term with the second order derivative. So let's write that down then. So what we have therefore is chi squared is equal to chi 0 squared plus, well, so what do we have? We have a 1/2, and then we have the second derivative of chi squared with respect to, oh, sorry. I think I've been drawing my second derivatives wrong, haven't I? This square should be daj squared. Okay, so this should be daj squared. At aj is aj star. Okay, and then we still had this aj minus aj star squared term here. All right. So in general, you know, if this chi squared function has a complicated shape, you know, I might not know exactly what this is, but it's just a number, right? You do the derivative, you sub in the aj star, and this comes out to be some number. So what I'm going to do is I'm going to define everything in these brackets just to be some constant b. All right. So if we do that, then we have chi squared is approximately chi 0 squared plus b
AJ minus AJ star squared. What kind of shape would this function have if I plotted chi-squared as a function of AJ? Like, just forget about AJ. What if these are x's, right? Yeah, it's just a parabola. This is just a quadratic function. So this is a chi-squared looks quadratic near its minimum. Okay, so if we imagine now plotting this thing, here's AJ, here's chi-squared. In general, it could have some complicated shape. And so here's AJ star, but near the minimum, we're going to have this parabola that would look something like this, right? So once I get too far from the minimum, then the shape of the chi-squared function can deviate from this parabola, but at least for values near the minimum, we get this parabola type shape. And so this thing is proportional to AJ minus AJ star squared. Okay. So fair enough. Then if I look at this expression in the red box, it governs the shape of this little parabola. And it has a bunch of unknowns, right? I don't know necessarily the true value of the minimum. So if we go over here, this is where I0 squared sits. I may not know exactly the value of AJ star, the value that minimizes this chi-squared. I probably have a good idea of where it is, but I may not know with great precision what it is. And I don't know this B coefficient that's sitting out front. So we have 1, 2, 3 unknowns. And so what we're going to want to do is we're going to try to determine those unknowns. And then what we're going to try to do is we're going to try to use one of those to estimate the uncertainty in our parameter. And let me tell you roughly what the resolution is going to be. So if B was really, really large, what would happen to the shape of this parabola? Let's say I took this parabola and then I increase the value of B. What happens to the shape? Yeah, it gets steeper, right? So if we had like a large B, we would get something that looks like this. So this would be a large B value. And then, of course, conversely, if we had a really small B, we would have something like this. Okay, so small b. The red one is the one that actually fits this minimum, but I just want to think about what happens if b was to change. So let's think about this. Here we're sitting at the minimum, and then if I move slightly away from the minimum, for the blue curve with the large b, chi-squared changes rapidly. So do you think that corresponds to us knowing the value of the best fit parameter very precisely or very poorly? Poorly. Well, let's think about that. If we go away and we increase chi-squared a lot, then that allows us to say, oh, okay, if I zoom in, like I know the minimum is sitting right precisely at this point. And so I know it quite accurately. It's actually this small b where we have a wide range of values that all give a pretty good estimate of the minimum.
And so now I have a big collection of A values that are, you know, all almost equally good minimizing this function. So I would argue then actually small b is when we don't know the position of our parameter accurately, and large B is when we do. Okay, so when B is large, the range of AJ values that minimize chi-squared is narrow. And so what I'm going to say is that we precisely know AJ star is fairly precisely known. And so that means that sigma AJ is small. On the other hand, when B is small, there's a large range of AJ values that come close to minimizing chi-squared. And so that means the value of AJ star is poorly known. And we have sigma AJ is large. Okay. It's going to turn out that the uncertainty in the best fit parameter is going to be inversely proportional to B. So we should expect that sigma AJ is in some way inversely proportional to B. We don't know yet if it's like sigma is just equal to 1 over B, or it's like 1 over B squared or something like that. Those details we don't know, but it seems like through this argument, that's roughly something that we should expect. Okay, so how much time do we have? Oh, 20 minutes. In principle, and in fact, in practice, if we know the value of chi-squared at 3 points of AJ near the minimum, we can determine the 3 unknowns. And those 3 unknowns were chi0 squared, AJ star, and B. And it's going to turn out this is the one that we really care about, the B. And so let's see how that would work, right? Essentially what we're doing is we have 3 unknowns here. We're going to try to set up a system of 3 equations so that we can work out what those unknowns are. Oh wait, so if we were to draw AJ chi-squared and just really focus in on values near the minimum, we would have this kind of parabola sitting here. And so what we're going to do is we're going to pick 3 values of AJ. So we can pick like A1, and then we'll pick A2 is equal to A1 plus, I don't know, delta A, and then we'll pick A3 is equal to A1 plus 2 delta A. And so maybe we pick A1 and it's sitting over here. And so here's A1. And when we select that value,
we measure a chi1 squared, right? Or not measure, like we just calculate, we know how to calculate chi squared. It's just the yi minus y of xi over sigma I squared, sum them all up for all the data points. And so we just pick a value of a1, we evaluate that sum, and we figure out what chi1 squared is. And then we go to over here, where we have a2 is equal to a1 plus delta a. This is delta a is our step size here. And when we do that, we calculate chi squared again, and we'll call that chi2 squared. And then we take another step, delta a, and I don't love my, I'm gonna adjust my drawing here so I can get slightly different values. So right here is going to be another delta a step. This is going to be a3 is a1 plus 2 delta a. And when we go evaluate our chi squared, we're going to find that over here we get chi3 squared. Okay, so now we have 3 values of the chi squared for different values of a. So we can write then, let's see, chi1 squared is equal to chi0 squared plus b, and then we have a1 minus a star squared. Okay. So what I'm going to do is I'm going to write a1 as a3 minus 2 delta a. So we could write this. Do I want to? Yeah, okay, I'll do that right now. So let's put in a1 is a3 minus 2 delta a minus a star squared. Okay. And so that's chi0 squared plus b. I'm going to write this in one more different way. I'm going to write this as a3 minus a star minus 2 delta a squared. And I'm going to call this equation 1. Okay. Chi2 squared is going to be chi0 squared plus b a2 minus a star all squared, which we could write as chi0 squared plus b. And a2 is going to be a3 minus delta a. So we could have an a3 minus a star minus delta a squared. Okay, good. And that's equation 2. And then chi3 squared is going to be chi0 squared plus b. And then we just have a3 minus a star squared. And that's going to be equation 3. So these 3 equations, 1, 2, and 3, they involve all of the unknowns. They all have chi0, they all have b, and they all have a star. And so we could solve this system of equations for those 3 unknowns. I'm not going to do it, but I'm going to write down the results. So we can solve this system of 3 equations for the 3 unknowns. The important results is, okay, so the one that we really care about is B. And if you go and solve the system of equations, what you get for B is the following. So it's chi1 squared plus chi3 squared minus 2 chi2 squared divided by this 2 delta A squared, where delta A is just whatever step size you chose. You could write down expressions for the other unknowns, chi0 squared and A star. I'm not gonna bother because we're not gonna use it. Okay, and so I think I want to switch to the next set of notes here, if I can find them. Where did I put them? Here we go. All right. So what we're gonna do is we're gonna return to our likelihood function. Let me scroll back and I'll just show you where we're gonna go back to. We are gonna go back to all the way to number sign. So remember, we labeled this thing number sign. So we're gonna come back to this probability and we're gonna try to approximate this probability near the minimum of chi squared. And what we're gonna do is wherever we see chi squared, we're gonna put chi0 squared plus b times aj minus aj star squared. I'll show you what we're gonna put in. We're gonna put in this expression. And so let's call this star. So we're going to put star into number sign. What that will lead to is showing that B will be inversely proportional to the uncertainty in our parameter. And when we do that, and we know how to calculate B, we'll have our uncertainty estimates. Okay, so let's return to the likelihood probability. This was equation number sign. And so it was P of A1, A2 up to AM was equal to this product of delta y sigma I square root 2 pi exponential of minus 1/2 chi squared. And we're going to sub in equation star, which said that chi squared is chi0 squared plus b aj minus aj star squared, at least near the minimum of chi squared. Okay, so if we make that substitution, then we would say that our probability is going to be approximately this product out front, which I get tired of writing because we're not doing anything with it. But anyways, there it is. And then we have an exponential of minus 1/2. And now what we have to put in is chi0 squared plus b aj minus aj star. I'm going to run out of space here. aj star squared. And then we got to close that bracket and close that bracket. Okay, good. Because I don't want to keep writing this, we'll define this coefficient out front as A. Again, it's just some number, right? We know all of our sigma I values. Delta Y is sort of kind of an interval where we allow our probability like between these two ranges. So you could just calculate that it's just some number that's never going to change. Okay. All right. So then what we have is, let's see, A. Now we have an exponential of 2 terms. And so I can write the exponential of 2 terms as a sum of exponentials. So we could have the exponential of minus 1/2 chi-squared times the exponential of, well, let's see, b times aj minus aj star squared. We have a 1/2 and we have a negative sign, so it's something like that. All right. So fair enough. This is a chi-0, right? So that has to be a chi-0 squared. Again, this is just some number, the minimum value of chi-squared. So a times that exponential is just some other constant, and we're just going to define that to be a prime. Okay, so then our probability is a1 to am, and so we have a prime. The exponential of, I'm going to write it in this way, minus aj minus aj star squared over 2 times b inverse. So I'm just putting this b in the denominator. Now, if you look at this, this is starting to look like the same kind of Gaussian. Remember, the Gaussian probability distribution was mu minus x, something like that. So you have a difference between two parameters inside of square, and then it was divided by 2 sigma. And so we have 2, and we don't have a sigma, but we have a b inverse. And so you can see how we're going to relate this b parameter to the uncertainty in these values, in the aj value. Okay, this is of the form of a Gaussian distribution. And so the Gaussian distribution, say f Gaussian was equal to 1 over sigma square root 2 pi e to the minus, was x minus mu squared over 2 sigma squared. And so the x minus mu is like this. And then we have the 2 is there. And so the sigma squared is, this b inverse is playing the role of sigma squared in our likelihood function, which is a Gaussian. So the likelihood function becomes a Gaussian function of each parameter aj, and sigma j, well, sigma j squared is equal to that b inverse. So sigma j squared is equal to this b inverse, or sigma j is equal to 1 over the square root of b, and this is the uncertainty in the parameter aj, where we know how to calculate b. In fact, we did it. Where was b? There it is. Let's see. This is small. Oh. Okay, good. So there's only 2 minutes left, so I won't write anything else down. What we'll do next time, which won't be until Wednesday of next week, is we will summarize all of this stuff, and then we're gonna take a look and see if we can develop kind of more of a intuitive understanding of what chi-squared represents, and how we could sort of estimate what we think its value should be. So if we did a nonlinear fit to a set of data, we calculate chi-squared, the minimum value, what should that value be? And how can we understand how it should change as we move away from that minimum? So we've done some kind of quantitative analysis of that, a little abstract. So what I want to do is I want to be more qualitative and develop more of an intuitive understanding of these ideas. But technically, we now have a full set of guidelines for doing these nonlinear fits. We do a grid search to find that minimum. Now we have estimates of the best fit parameters. We calculate 3 values of chi-squared near that minimum where it looks quadratic. We can use those 3 values to calculate this B parameter, and the inverse of the square root of B is our estimate of the uncertainty. The way we get these 3 chi-squareds is we take one of our parameters and vary it a little bit away from the minimum. Then we get the uncertainty in that parameter. Then we go to the next parameter, vary it a little bit away from the minimum, get 3 new chi-squared values, calculate an uncertainty in that new parameter. We just keep doing that until we've done it for all of the parameters that we're trying to find. Okay, good. So that's it. We'll see some of you in the lab this afternoon, and for the rest of you, I hope you have a good 4-day weekend.
It's surprising day.
Sir,
Yes.
I had a bit of a printing error
Yeah.
where my numerical values, I lost the points here.
Okay.
Are printed out in here, which is illegible.
Right. It's assuming it's these things here, I guess that I was.
Yeah, like
Yeah.
that.
Right. Oh, yeah. These are all the numbers. Yeah. Okay. So here I can adjust this a little bit. I might deduct a little bit. It's just a small amount for like the difficulty in reading it. Yeah.
I could also send you like a better.
So these are the various okay, yeah, if you want to email me something that's easier to read, that would be good. So yeah, do that. Send me an email. And then so you got, can I keep this? So
Yeah,
so once I get your email, I'll read what's in here and make it fast.
Yeah.
Okay, cool.
hopefully they're actually right.
Yeah, all right, we'll see.